In this video, I want to show you my derivation of the dot product. And I'm going to actually use Robert's worksheet, but I'm not going to write out all the details. It just took me way too long to fill in all the pieces, so a lot of it I just do in my head mentally, and I don't write things out. First thing I wanted to do was remind you of what the dot product actually was. If we want to take the dot product of two vectors, they have to be of the same size. In my example that I've created here, I created two vectors that were of size 4, and the dot product is defined to be the sum of the component-wise product of the components of the two vectors. So in this particular case, the dot product would have been 3 times 1 plus 5 times 0 plus 0 times -1 plus 1 times 2. And this is the notation we often use for dot product. In this case, it was 5. So let's go through now and actually create a program segment that finds this dot product using the invariant from your assignment. Notice that there were many invariants that we could be using, and there are actually many different program segments that we could develop. I think there will be a total of 8, but I'm going to use the one that was from the assignment, which means that the invariant is the dot product is the sum of I from 1 to k, not including k, of xi times yi, and k is between 1 and n plus 1, including the endpoints. So the first thing I do, as recommended by Robert, is to figure out what the guard will be for this loop. And so I know the post condition. Really, to start off any problem, I would have figured out first, formulated the precondition and the post condition, and then the invariant, and then I would try to determine the guard. Notice that when we exit the loop, the invariant and not the guard must hold. If I compare the invariant and the post condition, this will help me find the guard. Notice they're not exactly in the same form, in that the range for the invariant was that I was between 1 but less than k, and for the post condition it was I was greater than or equal to 1 and less than or equal to n. I want them to be a little bit more aligned, so I'm going to write the post condition as 1 is less than or equal to I is strictly less than n plus 1, because being less than n plus 1 is the same as being less than or equal to n if we're dealing with integers. And so now I notice that the invariant and the guard match if k is equal to n plus 1. So not the guard should be the k is greater than or equal to n plus 1, which means the guard is the negation of k being greater than or equal to n plus 1. So the guard is going to be that k is less than n plus 1. Well, I'm going to write it instead as k is less than or equal to n, which again is equivalent to k being less than n plus 1. Okay, so that is my guard and my first step. The next step I like to perform is the initializations. But the first thing I need to ask is, what kind of commands do I have here? What kind of updates am I going to be doing? Well, what are the variables involved? Well, one of them is k, and the other is the dot product. So both in the initialization and in the loop, I'm going to be assigning values to those two variables. So in the initialization, I'm going to say d becomes and k becomes. In the loop itself, I'm going to have a command d becomes and another command k becomes. Okay? Now, again, let's focus on the initializations. That is supposed to be before we've done any work. We can initialize. And so if I look at the invariant, it's supposed to hold before I start the while loop, so it must take into account the initializations. No work done means that I is going to be an empty range. So I'm going to set k to be equal to 1, because if k is greater than or equal to 1 but less than 1, that's the empty range. Okay. Now if I'm trying to evaluate a sum over an empty range, I know it evaluates to 0. So I'm going to assign d the value 0. Okay. Now those are my initialization commands. To be sure that I picked the right ones, I really should prove that the precondition implies the weakest precondition of d becomes 0 and k becomes 1, the invariant. And I challenge you to do that. But I know that it works. I've hand waved that it works. Let's now go through and try to figure out the assignments for the loop. Well, what do I need to know? I know that, first of all, I'm updating k in the loop, and the way that this is working is k is incrementing, so eventually the entire range will be from 1 to n, including n. And so I know that inside of the loop I'm going to assign k the value k plus 1. Now I need to figure out how to update d, my dot product. So what I'm going to do is think about what needs to be done. I know that when the invariant holds and the guard holds, that should imply the weakest precondition of whatever update I'm doing to d, and that's going to be some expression, followed by the update that I do to k, should leave me in a state satisfying the invariant again. And this update to d could be a function of k. And so what I need to do is determine how to pick the expression for d to make this predicate true. I know that if I have the weakest precondition of a command followed by another, it's the weakest precondition of d becomes this expression, where its postcondition is the weakest precondition of k is updated to k plus 1 invariant. So I'm going to do a little side and say, hey, if I want to figure out what the weakest precondition of k becomes k plus 1 invariant, I know it's just a textual substitution. So in the invariant, when I see k, it is replaced with a k plus 1, and that leads me to the predicate that d is the sum of I ranging from 1 to less than k plus 1 of xi times yi, and k plus 1 is between 1 and n plus 1, including the endpoints. If I look a little bit more carefully at the sum, I can actually break the range, split it into two pieces, and if you look at it, I is greater than or equal to 1 and less than k plus 1 is equivalent to I is greater than or equal to 1 and less than or equal to k. So I'm going to split this range into the ranges where I is greater than or equal to 1 and less than k, or I is equal to k. So splitting the sum, I end up with the sum of I from 1 strictly less than k of xi times yi, plus, when I is equal to k, it gives me xk times yk. And then if I look at the interval for k plus 1 was between 1 and n plus 1, if I rewrite that and describe the interval around k, it must be between 0 and n. Or I could write it as k is either 0 or 1 is less than or equal to k is less than or equal to n. How does that help me? Well, if I go back and try to figure out the weakest precondition of the assignment, where its postcondition is the weakest precondition that I just simplified, in the predicate, since the command is an assignment, I do a textual substitution for the dot product, an expression which is a function of k, e of k. So this weakest precondition becomes e of k is equal to the sum over I from 1 to k, including 1 but not k, of xi times yi plus xk times yk. And 0 is less than or equal to k is less than or equal to n. Now, the invariant and the guard is supposed to imply this predicate. And so if I write it out and I compare the invariant, which had a subcomponent, that d is the sum I from 1 to k of xi times yi and an interval, and the guard, I notice the intervals will work out nicely in that you're going to have k equals 0, or the same interval that you end up with whenever you have, when you simplify, you get 1 is less than or equal to k is less than or equal to n. So that part of the weakening and strengthening is going to work nicely. In order to figure out what e of k is, when I compare, I notice that the assignment of d in the invariant matches the sum I from 1 strictly less than k of xi times yi. So it seems to me what I want to do is pick the expression to be the d in the invariant plus the extra term, x sub k times y sub k. That's my update. And so I end up with d becoming d plus x sub k times y sub k. Now, this is my program segment. To show that it actually holds, what I would need to do is to prove that, the invariant and the guard imply the weakest precondition of d becomes d plus xk times y sub k, followed by k becomes k plus 1 invariant. And I'm sure that it does. But again, I'll challenge you to make that more formal. So this was the building of the program segment that found the dot product using the invariant here. There are many other invariants that you can use, so you might want to try and challenge yourself to see what happens to the updates, or see what happens to the program segment if you choose other invariants.